Hello everyone, welcome back. From today onwards, we shall discuss about Module 5 of your Unix system programming subject. So that is inter-process communication. Okay. Basically, inter-process communication is nothing but the communication between two or more processes. Okay. So in this module, we shall discuss about how two processes will communicate each other, how one process can control another process using the application, and also how we can implement the inter-process communication between the processes. Okay. So the first concept is to discuss with the introduction of inter-process communication. As I told you, inter-process communication is nothing but the communication between multiple processes. Okay. So the Unix system, it allows one application to control another application by means of IPC. So that means by using this inter-process communication, we can, not exactly the process, one application can control another application. Okay. And also IPC enables multiple applications or several applications to share data between them. Okay. So without interfering each other. So inter-process communication means we are communicating between the processes. Okay. So thereby the data can also be shared between several applications. And also, so this is supported in all multi-processing systems, because multi-processing means more than one process. So multi-processing systems, IPC will be supported in all multi-processing system, but it is not useful for single processing operating system, because name itself says single processing, that means only one process will be used at a time. Okay. In that case, the concept of IPC is not applicable, it is useless. Okay. So there are several forms of IPCs that are supported by Unix system. So now let us look into those forms. The first one is half duplex pipes. Okay. Next, FIFOs, first in first out, full duplex pipes, named full duplex pipes, message queues, shared memory, semaphores, sockets, and then streams. So these are the different forms of inter-process communication that are supported by Unix operating system. So out of this, the starting 7, okay, so these are restricted to IPC within the same host. Okay. So these 7 forms are restricted to the inter-process communication within the same host. Whereas the sockets and streams, so these can be used for inter-process communication with the other processes that lies on remote host also. Okay. So totally these are the different forms of inter-process communication. So now let us discuss each of these concepts one by one. The concept is pipes. Okay. So pipes are the oldest forms of inter-process communication in Unix system. So they have got two limitations. The first one is pipes are half duplexed. Okay. So historically the pipes are half duplex, that means the data flows in only one direction. And the second limitation is, so the pipes can be used between the processes that have the common ancestor. So that means they should be related to each other. Only in that case there can be an inter-process communication by means of pipes between those processes. So thereby generally what happens is, a process will create another process by using the fork function, and then after that the newly created process will be the child process of that parent process. So thereby there will be a relationship between those two processes as parent and child. Only in that case the pipe can be established. So these two were the limitations which were found in the pipes. So pipes is the oldest form of IPC that is supported by Unix operating system, and we can create a pipe by using pipe function. Okay. So the prototype is like this: # include unistd.h and then int pipe, and the argument is int file descriptor of 2. So here the return type is integer. So if everything is executed successfully, a pipe will be created successfully. In that case, this returns 0. Okay. If there is any error, it returns -1. Okay. So the argument is file descriptor of 2. So here the file descriptor of 0, so this is used for reading, and the file descriptor of 1 is used for writing. And one more important point is, here the file descriptor of 1 is an input to the file descriptor of 0. So file descriptor of 1 will be input to the, file descriptor of 0. Okay. So now there are two ways of representing a pipe between the processes. So this is represented with the diagram like this. So here in two views we are representing the pipe. So here in the left hand side there is a user process, within that we have the pipe. So pipe will be created and the file descriptor will be file descriptor of 0 and then file descriptor of 1. Okay. As I told you, the file descriptor of 1 will be input to the file descriptor of 0. So that is why in the representation, so fd of 1 will be given as input to fd of 0. Okay. So this is within a single process. Okay. And in the next representation on the right hand side, we have the process. So here fd of 0 and fd of 1, and we have created a pipe here. Okay. So the input, so that means the fd of 1 should be the input to fd of 0. So this is represented by using the pipe like this. So fd of 1 is given here, and then this is given as input to fd of 0. So these are the two ways of representing the pipe between the processes. In this case, the pipe is represented only within the single process. In this case, between two processes. Okay. So the inter-process communication within a single process is useless, because the name itself says it should be inter-process. That means it should be between the processes. But what we are doing here, we have created the pipe in a single process. So that is why a pipe in a single process will be useless. Okay. Normally the process that calls pipe will call fork after creating the pipe. Okay. So this is represented with this diagram. So this diagram shows the parent-child relationship by using the half duplex pipe. Okay. So this is the parent process and this is the child process. So once after the creation of the pipe, the parent will create the child process using the fork system call. So here the parent process has the file descriptor of 0 and then file descriptor of 1. Okay. So this is it is used for reading and this is used for writing. Similarly here in the child process also we have fd of 0 and then fd of 1. This is for reading and fd of 1 is for writing. Okay. So again fd of 1 should be input to fd of 0. fd of 1 should be input to fd of 0. Okay. So this is the representation of parent-child relationship. Suppose if we want to flow the data, I mean communicate the data from parent to child, that means the pipe should be from parent to child. In that case, we have to close the reading end of the parent process and writing end of the child process. I will repeat once again. if the data has to be flowed in the pipe from parent to the child, from parent to the child. In that case, so the reading end of the parent process has to be closed and writing end of the child process has to be closed. So this is represented with this diagram. So here we have created a pipe with the flow of data will be from parent to child. So from parent to child, right? So FD of 1 of parent should be the input to FD of 0 to child. So as I told you, we have to close the read end of the parent process. Okay, I have closed the read end of the parent process and then write end of the child process. So I have removed the write end of the child process. Similarly, if there has to be flow of data via pipe from child to parent, okay, so here from child to parent, in that case what should happen? From child to parent, right? So in that case the read end of the FD of 0, I mean the read end of the child process has to be closed, okay, and then the write end of the parent process has to be closed. So we will repeat once again. If there has to be flow of data from child process to parent process, in that case the read end of the child process has to be closed and then the write end of the parent process has to be closed. So what will happen? The data FD of 1 will be given as input to FD of 0 in that case, okay. When one end of the pipe is closed, in that case two rules will apply, okay. So we have discussed about pipes. So when one end of the pipe is closed, the two rules has to be applied. The first rule says that whenever a read operation is performed from that pipe where the write end is closed, okay, in that case the read operation returns 0, okay, returns 0 indicating the end of file. That means there is nothing to read from that pipe, okay. So similarly the second rule says that if we want to write into the pipe where the read end is closed, okay, in that case a signal called SIG pipe will be generated. So even if we ignore the signal or catch it or handle this signal using the signal handler, the write function it will return -1, okay, and with the error status flag set to E pipe. So these two are the rules that has to be followed when one of the end of the pipe is closed, okay. So now let us discuss about how we can create a pipe with a program. So this program illustrates how we can create a pipe and then how the pipe will be established from parent and child for the data flow from the parent and child, okay. So this is the include statement, main functions, and we have declared the variables. So here very first we are creating the pipe by using the pipe function and we are passing the file descriptor. Actually file descriptor is an array of integers. So file descriptor of 2, we have already declared that, okay. So if it is executed successfully, a pipe will be created between the two processes. Otherwise there will be an error, it returns -1. So if it is less than 0, in that case an error message will be printed by using pipe error, okay. So after this, after creating the pipe, if you remember I had told you that, so normally a pipe will be created and then the parent process, I mean the process will be forking the child process, right. So after creating the pipe, we have created the fork, we have invoked the fork function for creating new process, okay. So the fork function returns the PID, we are assigning that to the variable PID which is of type PID underscore T, and if it is executed successfully, no issues, the process ID will be assigned to PID, okay. Otherwise it returns -1. So in that case it will be less than 0. So if there is any error, we are printing the error message, okay. So later here, else if PID greater than 0, that means if it is executed successfully, we are just checking whether the PID is greater than 0. So if it is greater than 0, it indicates that parent process. Okay. So we have already discussed about the fork system call in module 3. So it returns two types of PID. So here if it is greater than 0, then it is the parent process. Okay. So here what we have to do, if you remember just now in the diagram I had showed you that for the data from parent to the child, what has to be done? The read end of the parent has to be closed. That means FD of 0 of parent has to be closed. Okay. So for parent I am closing FD of 0. Fine. So next what we have to do? We have to enable FD of 1 in the parent process. Okay. So that is why FD of 1 is nothing but writing operation. So that is why I am calling the write function. So write function we have discussed in module 2 itself. So this is the API. So that writes the data from particular buffer. This is the number of bytes to the particular file. Okay. So for FD of 1 we are just writing hello, and then the total number of bytes we have just mentioned it as 12. Okay. So write will be enabled. So that means FD of 1 will be enabled. This is for parent process. Then what about the child process? So previously in the diagram I had told you that in the child process we have to close the write end, but we have to enable the read end. So write end closing means FD of 1 has to be closed. So for child process we are closing the FD of 1. So after that we have to read. Okay. So read from this file. So from which file? FD of 0, that has to be enabled, and line. So this is an array here. Okay. Max line means somewhere we can mention by using hash define. So the number of bytes that has to be read from this file. Okay. So this read function returns the number of bytes that are successfully read. Okay. So that is why we are storing that into the variable n, which is of type integer. Okay. So in the next step we are printing the content that has been read to the standard output. Okay. So just we are displaying it in the console. So for that purpose we are writing into the standard output here. That is it. So this has nowhere related to the FD of 0 and FD of 1. We are just printing it, this read data, into the console. Okay. So that means the standard output. So we are passing write standard output file number comma line, that means the buffer to which the information is read, and then n, that means these many bytes of data is printed on the console. Okay. So this illustrates the concept of pipe. So now let us move on to the next concept. The next concept is Popen and Pclose functions. Okay. So just now in the previous example we have seen that whenever we are creating a pipe from parent to child for data flow, okay, in that case what and all we are doing, first we are creating the pipe and then we are forking the child process, and after that we are closing the read end of the parent process, we are enabling the write end of the parent process, and also we are closing the write end of the child process and we are enabling the reading end of the child process. Okay. So all this stuff is carried out in different functions. Okay. So these functions can be carried out by using only two functions, that is Popen and Pclose functions. Okay. So Popen and Pclose functions will perform all the actions which I have told you just now, like what and all we have done for creating the pipe, fork, closing the read end, enabling write end, all those actions will be performed by these two functions. So generally these two will perform creating the pipe, okay, and then what we were doing, we were forking a child. So again these two functions will perform the same, and then closing the unused ends of the pipe. So we have disabled the reading end of the parent process, right? Same way here, by using these functions itself we are closing the unused ends of the pipe and then executing a shell to run the command. So we have to execute the shell in order to run the command and then waiting for the command to terminate. So all these actions will be performed by only these two functions itself. So the prototype of Popen and Pclose functions is represented like this. So the header file is stdio.h. Fine. So the first one is popen function. Name of the function popen, that means pipe open. So this returns, the return type is file pointer. So if it is executed successfully, it returns the file pointer. Okay. So if there is any error, it returns -1. It has got two arguments, the command string and then the type. So the command string indicates the command that has to be executed on the shell, whereas the type indicates whether the read or write mode. Fine. So next, the pclose function, the return type is integer. So if this function is executed successfully, it returns the termination status of the command string, because so we will be waiting for the command to terminate, right. So if it is terminated successfully, the termination status will be returned. Okay. If there is any error, it returns -1, and we are closing that particular file that is referred by this file pointer. Okay. So these two are the function prototype of popen and pclose functions. Both are included under stdio.h header file. We have discussed about popen function and pclose function, right, and the importance of those two functions. So generally the popen function, so this will be first forking the child by using the fork function, and then it will implement exec system call in order to execute that particular command string. Okay. So this is represented with this diagram. So here the first one, so it indicates whenever the command string has to be executed with the type R, that means in the read mode, in that case the file pointer will be connected to the standard output. So the same thing is depicted in this diagram. So we have the parent process and then the child process, wherein we have the command string. Okay. If this has to be executed, then the file pointer will be connected to the standard output. So this will be connected to the std out. So this is the result of the fp equals popen. So as I told you, popen returns the file pointer. So that's why we are assigning it into file pointer. So fp equals popen. So we have command string comma R. That means the type. Okay. So next, if we have used popen with command string comma W, in that case the file pointer will be connected to the std in, that means the standard input. So the same is represented in this diagram. So parent and then the child, so command string refers to the child process here, and file pointer will be connected to the standard input. Okay. So here, so this will be in the reading mode, right. So it will be reading mode. So that means from here it has to be passed on here. Okay. So from here to this one. So in that case, so the standard output what was there, from that it returns the file pointer. Similarly, so from parent to child for writing, so from here to here for writing purpose. So that's why from that particular file, so we are writing into this std in, so standard input. Okay. So this is all about popen and then pclose functions. So now let's look into the next concept. So the next concept is co-processes. Okay. So before getting into the co-processes, first let us see what is a filter. Okay. A Unix filter, in a Unix system, a filter is nothing but a program so that reads from the standard input and that writes into the standard output. Okay. So any program, a program that reads from the standard input and writes into the standard output will be treated as filter in the Unix operating system. So a filter becomes the co-process whenever the same program will make use of the filter's input and then it will generate the filter's output. So understand properly, co-process means the process which has the same functionality as that of the another process. Okay. So here, so any filter can become a co-process if the same program will read from the filter's input and then generates the filter's output. Okay. So basically a co-process will be a program that will be running in the background of the shell, and its standard input and then standard output will be connected to the another program through pipes. Okay. So a coprocess is nothing but a program that runs on the background in the shell. Okay. Its standard input and standard output will be connected to another program through pipes. So here we have the diagram. So this process will create two pipes. Okay. So any process will create two pipes now. So one is between the first process and then from the standard input and the coprocess, and another will be between the standard output and the coprocess. Okay. So the same thing is represented in a diagram like this. So we have the parent process and then the child process. So let it be the coprocess here. So as of now, the writing end, the FD1, so that means the first process. So this will be connected to the STD ins, that means the standard input via the pipe 1. Similarly, the standard output will be connected to FD2 of 0 using pipe 2. So that means the second pipe. So the process creates two pipes. One is the standard input of the coprocess and another will be the standard output of the coprocess. So now let us discuss this concept with the help of a program. So this program is used to create a simple filter for adding two numbers. Okay. So we have included header file and then main function. We have declared three variables, n and two numbers, I1 and I2, and then a buffer of type character line. And very first we are calling the read API from the standard input. Okay. So from the standard input we are invoking the function called read. So if it is executed successfully, it returns n. So n is the number of bytes that is read successfully. Okay. So in that case it will be greater than 0. So I am just checking at the end I am terminating with the null. So that's why I am initializing it with a 0. So now scanf, I am just checking scanf. Scanf I have already told you in the previous sessions. So this is similar to scanf, but the difference is we will be reading the input from the formatted string. Okay. So from the formatted string means that was already read and placed into the character array line in the previous read. Okay. So here it contains the string, nothing but the numbers which we give it as input. So that will be stored in this line array. So from this line array we will be reading two numbers, I1 and I2. Okay. So if it is read successfully, it returns the total number of read inputs. So here in this case 2. So if it is 2, then it is successful. In that case we are making use of sprintf. Sprintf means again we are printing into some formatted string. So here we are printing, what we are printing? I1 plus I2. That means two numbers, the addition of two numbers, the result, the sum is placed into the string line. So now we are checking the string length of line. Okay. So later, next what we are doing, we have to write this into standard output. So we are invoking this write system call and we are just ensuring whether it is executed successfully or not with the logical condition. If it is not executed successfully, we are printing the error message. Okay. So this is if the scanf is executed properly. Suppose the input is not given properly, in that case what has to be done? We have to say that invalid number of arguments. Okay. So if it fails, if it is executed successfully, then fine. That means the arguments are given in a proper way. Okay. Suppose if this fails, else portion will be executed here. So what we have to say? We have to print in the console that invalid arguments. So for that we are making use of write function. In the we are writing into standard output saying that invalid arguments. Okay. So if it is executed successfully, so successfully it will be written. This message will be written to the console, the standard output. there is any error within this write API itself, in that case we are printing that using the error message. And finally, we are closing this else condition and we are closing this while. Okay, and then program is terminated with a exit of 0. So this is for creating a filter for adding two numbers. So what we are doing here, first we are reading the input that is given through the console and we are reading that to a array, character array called as line. So next step, from that line we are scanning two inputs, we are reading two inputs, and after that we are printing that sum into that particular line, array. So now from that character array we have to print to standard output, right? For that we are making use of write system call to standard output, and this is the error conditions we have handled. That means if the input is not given properly, then we have handled that also in the program. Okay, so in today's class we have discussed about the inter-process communication. So what exactly the inter-process communication, and then the different forms of IPC that are available in Unix operating systems, and then we have started with a discussion starting from pipes. Okay, so half duplex pipe, so how the pipe will be created between the parent and child with the data flow from parent to child and again from child to parent. We have discussed with the program also, and later we have seen the concept of Popen and Pclose functions and then the co-processors concept. Okay, so hope you have understood all the concepts. So we shall continue in the next session. Thank you.